So in this video, we're going to have a look at the definition of the limit of a sequence of vectors in Rn, i.e. real n space. So we're going to start off with a sequence then, and these are just like sequences that we've seen before, except that the terms of the sequence are now vectors in some Rn. And we're going to do this for a general n, so I'm not going to specify what n is, but it's some natural number. Now, I'm going to denote the terms of the sequence now by superscript rather than subscript, and that's because I'm saving subscript for the components of the vectors. So x1 is itself a vector and will have n components, and I'll denote the first component, x, will have the one superscript, but then we'll have one subscript to denote the first component of this first x1 vector. And then if the subscript is 2, that'll be the second component, and it will go all the way to n, which will be the nth component of that vector. So that's the reason I've moved from denoting the terms of the sequence with subscripts to superscripts. So formally, of course, the way that you capture the information of a sequence is that the sequence, which we might call the sequence x, is a mapping from the natural numbers into your real n space, Rn. So 1, 2, 3, we start the natural numbers at 1 rather than 0, and what the first number is being mapped onto, so what 1 is being mapped onto, will be some vector in Rn, and that will then be the first term of your sequence. Then what 2 is being mapped onto, it'll be mapped onto some vector, and that will be the second term in your sequence. So this is formally how you capture the information that we intuitively write out like this. So we say that the sequence of vectors is convergent and has a limit if it obeys a certain epsilon criterion, and we'll go through what that is in just a moment. Notation-wise, it's very similar to sequences of real numbers. In fact, it's the same. So we write limit as, and I've used m rather than n just because we've already used n for the dimension of our real space. So limit as m approaches infinity of our sequence xm, where this is the sequence of vectors, is equal to L, where L is our limit, and this limit isn't of course going to be a real number, it's going to be a vector itself. Our sequence is of vectors, so the limit is also going to be a vector, and so L is going to be an element of Rn. So the epsilon definition now for this sequence converging to this limit L is that for all epsilon greater than 0, where epsilon is a real number, there must exist a natural number big N such that if little n is another natural number that's greater than or equal to big N, and you look at the distance between your vector x little n in your sequence of vectors and the limit, i.e. the norm of the difference between the two, this is less than epsilon. So to get intuition for this definition, we'll use R2 because it's the easiest to draw a picture for. So here is R2 represented with the plane. We've discussed in previous videos the correspondence between the abstract structure and the intuitive picture. So let's say here is our limit vector L, and then what I've drawn here is I've taken some epsilon that's greater than 0, and I've drawn on here what is the epsilon neighborhood around L, which is all the vectors in R2 that are a distance away from L less than epsilon. And then what this definition here is saying is that there must exist some big N, there must exist some point in our sequence of vectors, which is, I've put here, x big N, such that if you go to that point or beyond that point, so if you look at all the vectors from here onwards, they are all a distance away from L less than epsilon, meaning that they're inside this epsilon disk, this epsilon neighborhood around my limit vector. So, and that holds true no matter what epsilon you take. So however small you make this, you can always find a term in the sequence such that it and all the terms beyond it are within that epsilon distance. So this epsilon definition is still capturing the fact that the sequence of vectors gets and stays indefinitely close to the limit vector. So I've just drawn a little bit of that on. I've put some dots in there to represent these vectors in this tail end of the sequence. So just to stress this again, it's saying however close you want to be to the limit, there does exist a term in the sequence that is that close, but moreover, all the things beyond it are also that close. So it's saying that, yes, your sequence of vectors gets however close you want to the limit and stays that close to the limit. And that captures the intuitive notion of our sequence of vectors converging to this limit vector L. So it is of course very similar to the definition for the limit of a sequence of real numbers. The difference is that the notion of the distance between the terms of the sequence and the limit has changed. It's no longer just the absolute value, instead it's now the norm, which is taking the place of the absolute value. And of course, when I say norm here, I mean the Euclidean norm on the n-dimensional real vector space. Whenever I talk about real n space, I mean the n-dimensional real vector space with the Euclidean norm. So the next thing that I want to do is talk about the coordinate sequences and how convergence of the coordinate sequences relates to the convergence of the overall sequence of vectors. So each one of the terms in my sequence is itself a vector, and I now want to actually write them out as full vectors with all of their components written out. And this is the reason that I superscripted which term we are, because I want to subscript what component we are. So this is my sequence written out in full now. I'm using column vector notation here just because it looks better. I'll flip between notating vectors as row vectors or as column vectors. It doesn't really matter. It just looks better as column vectors in this context. So my vector x1 written out with its n components, then we're back in arbitrary Rn now rather than this picture example which was R2. So here is the first vector, so you can see all of the components have the superscript 1, and then the subscript is denoting which component we are. So this is the first component, this is the second component, and it goes on down to the nth component. And then here is the second term of the sequence, the second vector, so superscript changes to 2, and then again we have the subscript denoting the component, so x21, x22, x2n, all the way down to x2n, and then this is the third vector here. Now, the components of the vectors, we can also call them the coordinates of the vectors. So this is the first coordinate, this is the second coordinate, this is the nth coordinate. It's equivalent terminology. Coordinate, component, we can use either of them. So what I can now do is consider the coordinate sequences, which are sequences of real numbers. So I build these. I build, for example, the first coordinate sequence by just taking from each of the vectors in my sequence the first coordinate. So I've done this here. So I've got x11, so that's the first coordinate of the first vector. Then I've got x21, that's the first coordinate of the second vector. Then x31, the first coordinate of the third vector, and it would continue on. I'd take the first coordinate from every single one of the vectors, and I'd then of course have just a sequence of real numbers. I can also construct the second coordinate sequence. So here it is. I've taken the second coordinate now from each of the vectors and made a sequence of real numbers. So you can see all of the components or the coordinates are set at 2, and then which term or which vector I've taken it from progresses. And I can continue this on. I can do this for every single one of the coordinates all the way down to the nth coordinate, and here is the nth coordinate sequence. And my question is now, if the sequence of vectors converges to some limit vector, will the coordinate sequences also converge to some real number? And in particular, will they converge to the corresponding component of the limit vector, i.e. will this converge to the first coordinate of my limit vector L, and will this converge to the second coordinate of my limit vector L, and this converge to the nth coordinate of my limit vector L? And the answer is of course yes, but we want to prove that. So to prove this then, let's start with the assumption that the sequence of vectors does converge, and it converges to the limit L, and I've written the limit vector L out in full here with all of its coordinates, so L1, L2, all the way down to Ln. And what I'm now going to do is I'm going to take this first coordinate sequence here, which I'll denote like so. So I've put in 1 here for my coordinate, and then I'm letting this progress on. So we've got n here, so this is a sequence of real numbers as n progresses up the natural numbers. And I want to show that this converges to the corresponding component of my limit vector, which is the first coordinate, so I want to show that it converges to the real number L1. Now, we're doing this for the first coordinate sequence, but you'll see that none of the argument here is specific to the first coordinate sequence, and indeed could have been applied to any of the coordinate sequences, to the second one, the third one, all the way down to the nth one. So you'll see that from this argument it clearly is going to also follow for all of the coordinate sequences. So to prove then that this sequence of real numbers converges to this limit, remember the epsilon definition for the convergence of a sequence of real numbers. I need to take an epsilon that is greater than 0, and I then need to find a big N in this sequence of real numbers such that at that term, and for all terms beyond it, they are within epsilon distance of my limit L1. So how am I going to get that big N? Well, I know that the epsilon definition for the convergence of this sequence of vectors is satisfied, so I will get my big N using that. So applying my epsilon that I've got here to my epsilon definition for the convergence of my sequence of vectors, I can find a vector x big N such that if you go to it or any of the vectors beyond it in the sequence, they are within epsilon distance of my limit vector, i.e. the norm of x little n minus L is going to be less than epsilon if little n is greater than or equal to big N. Now, I have realised that up here I deliberately used m rather than n because I didn't want it to get confused with the dimensions of my space, and then I've abandoned that thoughtfulness and now I'm just using little n and big N all over the place again. Please don't get confused, obviously, between the little n's that are here, which represent the dimension of the space, and then the little n that's here, the little n that's here, the little n that's here, which is part of the sequence notation. It's just the normal letter that is used in sequence notation, and therefore I just went on autopilot to use it without realising that I'd already used it here for the dimension of my space. I'm sure you're going to be able to cope with it though, just don't get confused between where we're using little n to mean the dimension of the space and little n to mean something about the sequence. So I'm now going to use the big N that I've got here, and I'm going to show that it works for the definition of convergence of my sequence of real numbers to converge to this, i.e. there'll be a corresponding big nth term in my coordinate sequence here, and I want to show that if you go to that term or beyond it, so if you go to a term little n that's greater than or equal to big N, then the distance between the term of my sequence xn1 and the limit L1, modulus now because they're both real numbers, is going to be less than epsilon. So I want to show that this is less than epsilon, and what I know is that if you look at the distance between the whole vector xn and the whole limit vector L, that this is less than epsilon. So I want to go from this to knowing this. So now it's time just to remember the definition of the Euclidean norm and use it. So firstly, let's just write out these two vectors in full. So in full, this vector is xn1, xn2, all the way down to xnn, and this is where the notation's getting really a little bit confusing because of the fact that the two n's appear here where they're meaning totally different things. I'm sorry, it's too late to stop now, but don't get confused. This is the n referring to the dimension of our space, and this is the n referring to our term in the sequence. And then we've got our vector L, which written out in full is just L1, L2, all the way down to Ln, and then we're subtracting those two vectors off, so this is the vector that we get overall. And we want to take the norm of that, so we just need to now apply the definition of the Euclidean norm. So the Euclidean norm then of this vector is the square root, and then we've got the sum of the squares of the coordinates. So the first coordinate is xn1 minus L1 squared. The second coordinate is xn2 minus L2, and then we need to square that. And then it continues on all the way up to the nth coordinate, which is xnn minus Ln squared. So that's the Euclidean norm, and that's going to be less than epsilon. So from the fact that this thing is less than epsilon, I want to be able to derive that xn1 minus L1, the modulus of that real number, is less than epsilon. And here's that thing appearing in this great big norm expression here. So how am I going to get that? Well, the first thing I'm going to do is I'm going to square both sides to get rid of the huge square root that's complicating things. So I've squared both sides of my inequality. The square root sign has now gone, and on this side epsilon has become epsilon squared. Now, when you have an inequality and you square both sides, as long as the two sides were positive to begin with, then the inequality remains true. If one of them is negative, you can run into problems. So you could, for example, have the inequality -2 is less than 1, which is true. And then when you square both sides, you then get 4 is less than 1 squared, which is 1, which is not true. But as long as you have positive numbers on both sides of your inequality, then when you square it, the inequality stays the same. And the things that we had were positive. Epsilon was positive, and the square root of this, the square root is always a positive value, so it was positive as well. Now the next thing I want to do is get rid of all of the coordinates that I'm not interested in. In the example that I'm doing, which is the first coordinate sequence, I'm only interested in this bit. If I was doing one of the other coordinate sequences, this is the part where I'd do it differently. I'd take the bit that I was interested in. But as I'm doing the first coordinate sequence, I'm not interested in this bit, not interested in all the bits in between here, and not interested in this bit. So I'm looking to get rid of them, and I just want this bit in an inequality with epsilon. And I can do this quite simply by noting that xn1 minus L1 squared, this bit here, is always going to be less than or equal to the whole thing, because of the fact that this is a sum of squares. Squares are always going to be non-negative, and therefore the smallest that the rest of this could be is possibly all of these could be 0, in which case you'd have equality, but if any of them aren't 0, then they'll be positive, in which case you'll have that this is less than this. But you can always say that this thing is going to be less than or equal to this sum of squares. And so by transitivity I can now conclude that as this thing is less than or equal to this whole sum thing, and this sum is strictly less than epsilon squared, then I can conclude that this thing must be strictly less than epsilon squared. So xn1 minus L1 squared is strictly less than epsilon squared. And now this is looking very hopeful. All I need to do now is take square roots. So taking square roots of both sides then, xn1 minus L1 squared becomes the modulus of xn1 minus L1. It doesn't just return to being xn1 minus L1, because that might be a negative value. When you square it, it becomes a positive thing, and then when you square root that square, it doesn't take it back to the negative value, because the square root by definition is a positive function, or a non-negative function. It's 0 for 0 input. But it will take it onto the positive version of itself, so you do need to have the modulus signs there. And then epsilon squared, when we square root that, it just goes back to epsilon. So both of the things on both sides were non-negative numbers, so we can take their square roots, and this is what we're going to get. The inequality is also going to hold true when we take square roots, because of the fact that the square root function is a strictly increasing function. So if the inputs had a certain inequality, then the outputs will also obey that inequality. And then what we've got here is exactly what we wanted. So what we've basically done is we've shown that if the whole vector is within epsilon distance of the limit vector, then the first coordinate must be within epsilon distance of the first coordinate of the limit vector. And this argument works for all the other coordinates as well. You'd go about it exactly the same way, except at this stage, instead of picking the first one here, if it was the second one you were doing, you'd have the second one here, or if it was the third one, you'd have the third one here, all the way up to the nth one, you'd have the nth one here, and you'd be able to then conclude that this, with whichever coordinate you want, is strictly less than epsilon squared, and then by square rooting it, you'd get the corresponding expression with whichever coordinate you want here. So we could change this to the ith coordinate, if you like, where I ranges from 1 to n, little n, where little n is representing the dimension of our real space. So what we've done then is shown that if the sequence of vectors converges to a limit vector, then all of the coordinate sequences will also converge, and they'll converge to the corresponding coordinate in the limit vector. We'll have a break here, and in the next video we'll show the other way round, which is that if all of the if all the coordinate sequences converge, then you can conclude that the sequence of vectors converges.